Okay, so this is week 11 and we will be, I think today we will finish the syllabus for this course, yeah, which will end in a characteristic function, okay? So after that, you can do some revision, all right? And then week 13, 14, you already start to have your part 1 of your final exam 1 and part 2 of your final exam 2, okay? So yeah, so we're finishing today. Okay, so let's just refresh a little bit about the characteristic function, right? So we have the characteristic function defined as this expectation, right? Where you have, you basically have a complex number, I, okay? So this is a complex, oops. So this is a complex number. I equals to square root of -1. All right. So the reason why we want to use characteristic function is because it always exists, right? And uniquely characterizes a distribution, right? Characterizes a distribution, okay? Which means it's like some kind of a barcode, right? Each well-known distribution has a characteristic function. So if ever you find a particular characteristic function that is that has a known form, then you can imply that the identity of that distribution. Okay. Compared to moment generating function, as we have shown last week, does not exist for certain distributions, right? Okay. The reason is because it is unbounded for certain distributions, but this will always exist, okay? And then you can find moments, finding moments from the characteristic function, right? So your characteristic function, basically, if you use Taylor series expansion, right, on the exponential function, so basically you will get 1 plus itx plus itx squared, okay, 2 factorial and so on, right? And basically this is, if you write it in concise form, it is in this way, okay, in sigma notation. So if you take the derivative, right, you take d of dt by t. So basically you can move the derivative sign inside this expectation operation, and that will give you, so you differentiate this, so you're going to get, so your n will become 1, okay, and this will, let me use, okay, n minus, so this should be -1, okay. This will be I power of n and then t power of n minus 1, right? Okay, because you are differentiating with respect to t, right? So this n comes down and it cancels with the n term here, so you get n minus 1 factorial. So you subtract 1, right? But instead of starting from 0, you start from 1 now, because this has to be at least 0, okay? So, and therefore, if you substitute 0, right, t equals to 0. So what's going to happen is that, so here the first term here is basically just I power of n, so it's 1. So x power of 1, right? The rest of them will become 0 because they will involve t, yeah? And your t is set to 0, right? So then, therefore, you can find your expectation of x as the derivative of 0 divided by I, okay? It's very easy to see from here that if you differentiate it k times, okay? Differentiate it k times, you will end up with so n equals to k, I power of n, t n minus k. This will be n minus k factorial, okay? X power of n, right? So again, it will be the same. So here, usually we use the shorthand, right? So differentiate k times, you set to 0. This will be just, you are left with the first term. So the first term will be I power of k, expectation of x power of k, right? And therefore, your kth moment is equal to the kth order derivative, right, evaluated at 0, divided by I power of k, okay? So it's similar to the moment generating function, in the sense that you differentiate the moment generating function k times, set t to 0 to obtain the kth moment, right? So in this case, you also do the same, except that you just have to divide by I power of k, yeah? Okay, there is an additional term. You have to divide by a complex number here. Right, okay, so that's some recap on the theory. Okay, and then we have two important results related to characteristic function, okay? The first one is called the inversion formula. The inversion formula allows you to get the probability density function from the characteristic function, right? So it's an inversion, right? Just now we can construct characteristic functions when we have a PDF, right? So it will be useful if we could actually reverse the process, right? That's why it's called an inversion formula. The formula is given by the following. F of x is equal to 1 over 2 pi integral. Okay. Now, strictly speaking, this is a kind of complex integration, right? But as I mentioned, it's actually not possible to do the actual complex integration if you have not had a course in complex variables, okay? And that course itself takes at least half a semester in order for you to know how to do some complex integration. So generally, unless you have taken it somehow because of some coincidence, otherwise, over here, we basically only will deal with some particular examples of inversion, where if you assume the integral is real, then you get the same result as what you would actually get if you had done complex integration, right? So we only look at those examples, okay? So the inversion formula, let's try out some examples, okay, on using the inversion formula. Okay. So let's look at an example here. So we look at the normal, the standard normal, okay? The standard normal has characteristic function given by e minus t squared over 2. If you recall, the moment generating function of the standard normal is equal to e of, well, in general, for n mu sigma square, it is mu t plus sigma square t square over 2, right? So therefore, so for general case, right? Therefore, when your mu is 0, sigma square equals to 1, you will end up with e, will be e of t square over 2. Now, why do you have a negative here? Because remember, your characteristic function replaces t with it, right? So basically, from here, you have e of it squared over 2. So you have e of minus t squared over 2, right? So basically, you can actually get the characteristic function, all right, of various distributions by going to their moment generating functions, right, if they exist, okay, and then simply replacing the t with it, right? That will save you a lot of trouble, okay? Only in cases where if the moment generating function does not exist, does not exist for a particular distribution, then you have to start from scratch, right, and work out the characteristic function according to the definition of characteristic function, right? Otherwise, basically you can basically just use this approach, right? Replace t with it, okay? Replace the t in moment generating function with it, okay? So you have this. And we are interested to see if we can actually recover the standard normal probability density function if we have the characteristic function, right? Let's try, right? So the fx is equal to 1 over 2 pi of this e minus itx times e of minus t squared over 2 dt, right? Now, when you see this kind of exponential forms, right, and then you got a square, this has this is kind of like it's quadratic in t, right? Immediately you should recall the usage of the completing the square method, okay? So you basically try to factorize, right? This will be t squared. This will be, okay, you have a plus. Okay, just a minute, yeah. The inversion formula. Okay, great. So you have I minus I t x, okay? There will be a 2 here, okay? Right, okay, so I have just take care of the sign, right? The minus, you get positive, and then you have a minus here, so that you get a, or maybe at this point, I will just keep it simple, just put it at plus. ITX, there's a 2 here, plus, okay? And then you factorize, okay? E of minus 1 over 2, you factorize as t plus ix squared, right? Okay, so when you expand this, you get t squared 2tix, right, which is this one. But then you get an extra term, which is I square x square, right? So you have to get rid of that by cancellation. Okay. But this actually helps you because this term here is not involved with t, so that's why you can take it out of this integral. Okay, that's the idea of doing the completing the square method, right? And then over here you have the form, the quadratic form, where this is basically you can view it as the part of the the density of a normal distribution. Okay, so then you can write it as this. So you can take out the e of. So over here you have the kind of a bunch of cancellations. So minus minus you get plus, I square you get minus, so you get minus x squared over 2. And over here you have 2 pi, right? So you kind of like donate half of it. It's kind of like you donate a square root of it, right? So you donate square root parts, so you are left with square root. Okay, you donate it to the integrand here, and then you basically have this thing, right? So t. So over here you kind of like write it as the following, right? Minus minus, right? Over 2 dt. Okay. So once you write it like this, then you basically will argue that this is the PDF of a normal with mean I minus Ix and 1. Strictly speaking, this cannot be done, right? Because the mean of the normal density actually lies on the real line, right? So it doesn't involve any complex number. Okay, so this is like kind of like a kind of a hack, all right? Because otherwise, as I mentioned, you have to make use of complex integration, and you have no means of doing that, right? So you kind of like say, okay, so this is like the PDF of a normal, and I'll just, if I think of minus Ix as the mean, this will be the PDF of normal, right? And then, of course, this will integrate to 1, and therefore I'm left with this part here, which is exactly the PDF of a standard normal distribution. Okay, so although here you kind of like sort of like cheated a bit, right? But then it gave you the same result. Okay, that would have cost you like at least half a semester to learn. Yeah, but of course this is basically just a hack, right? If you really want to learn it properly, you still have to use complex variables. Okay, so here I'm just illustrating that in this case we had to resort to some kind of a hack. All right, for this case. Okay, I'll show another case where you don't need to use a hack. Okay, you basically can work out. Okay, but these kind of examples are a bit limited. Yeah. Most of the examples will require you to know complex integration. Okay, so this is for normal, and this one is for exponential. Exponential with mean 1. Okay, its characteristic function is 1 over 1 minus it. Okay, you can check that easily. Yeah. Okay, so that's left as an exercise. All right, you can check that. So our goal is to use the inversion formula to find the density, right? Which we of course know that it is just equal to this form, right? We just want to test out the inversion formula. Okay, so you basically have this. So e of minus it x, right, times 1 minus it, right, and dt. Okay, you don't have to feel strange that this integral is running from minus infinity to infinity, because it's with respect to t, yeah, not with respect to x. Okay, so take note of here that there's nothing strange with integrating from along the real line here. Although your distribution is restricted is maybe on the positive line because the integration is respect to the parameter t, not x. Okay. Okay, so from here, what can you do? Let me see. So, okay, sorry, not this one. Okay, sorry. Has to use the no, not the exponential. That one is a bit. That one will require complex integration. You have to use okay, Cauchy. All right. So we know the Cauchy density is 1 over pi 1 plus x squared. Yeah. X is on the real line. Okay. So okay, basically we have this. And you split it into two parts, right? One part is the positive part, so you'll run from 0 to infinity. So this will be e of minus I tx times e of minus t, right? So your absolute t becomes, is basically t when your t is positive, right? And basically minus t if your t is negative, right? So you have dt plus minus infinity to 0, e of minus I tx times e of, so you got minus, so you got t, yeah? dt, okay? So this one here is easy. So you have e of minus t, right? 1 plus I x, okay? dt. So this one you make a change of variable. Let's say you change u, you change t equals to minus u, right? So your dt will be minus du, right? So over here, your minus infinity will become infinity because you put you reverse the sign. You got 0. So here is the, so you have e of I u x. So this will be e of minus u. This will be minus du. Okay. So over here you have basically e of minus t. So you treat this as a constant, right? Okay, this is a constant. So you have e1 plus ix. There's a negative here. So you evaluate. Now this part here is basically this negative will come here and it will flip this sign, right? So you'll get 0 infinity. So here you have e of minus u, 1 minus I u, okay? And this will be du. So here you will have minus e of minus u, 1 minus iu over 1 minus iu. Okay, evaluate at 0 to infinity. Okay. Right. Okay. So from here, we know that. So this thing here will be basically 1 over 1 plus ix, right? And over here, this is the same, plus 1 over let me see, it should be sorry, that's an, so this is an I, this is an x, okay, an x. Okay, so 1 minus ix. Okay, so this is an x, sorry. Okay, so you have these two terms here. So basically you multiply the denominators. So you will get this 1 plus is 1 minus, same term. So you will end up with plus minus, right? So you get an x squared minus I squared is -1 minus minus, you get a positive, right? So in the numerator, you have 1 minus ix plus 1 plus ix, so you will get a 2, right? So over here, remember we have a 1 over 2 pi, okay, which I kind of like left out at the beginning, okay, 1 over 2 pi, 1 over 2 pi, okay. So you have 1 over 2 pi, so the 2 will cancel, so you end up with 1 over pi 1 plus x squared. Right. So this shows you that this function, right, is the characteristic function of the Cauchy, because when you apply the inversion formula, you get the Cauchy density. Okay. So we will just look at this these two cases as examples of using the inversion formula. Okay. So then just to give you some awareness about you can also use characteristic function to compute probabilities. Okay, so here's the result. If the probability measure mu as characteristic function phi t, and of course, and if the measure at the singletons are 0, then the measure of so the measure of some interval here, right? The probability measure will be equal to 1 over 2 pi this thing. Okay. So so basically there's a formula to compute the probability here, right? But generally this result is not much of any much actual application use, because this evaluation is rather complicated. Okay, it will, I think almost sure that you will have to use complex variables to do it. Okay, so we're not going to, and in fact, it will be actually much harder to do than if you just directly evaluate from by using standard integrals anyway, right? So this is just to make the connection, just to establish some kind of connection, right? So we're not actually going to use it, but it may be of some theoretical use, especially like, let's say, for example, you want to find some kind of bounds, right? So from here, for this integral gives you some means of finding bounds, right? Okay, because you know that the integral, right? If you have some integral, okay, the integral of this is basically bounded by the integral of f. Okay, so basically this thing is so since your mu is the absolute of mu is positive anyway, so this is directly bounded by, you know that this will be bounded by this term. Of course, that includes the BT. Okay. So I think your phi t is always positive. So it can come out here. So you can actually work with some inequalities here, I think. All right, depending on what is the actual form, right? What is the actual form of phi t, and what are the values of a, b, right? So you might be able to work out some bounds if it is necessary, right? But we will not go beyond that in this course, right? Just to mention that characteristic functions can also be used to compute probabilities. Okay. So now we can actually talk about IID cases, right? So basically, let's say if x1, x2, xn are IID, random variables with characteristic function phi t, therefore they are sum, right? Is equal to e of I t x1 raised to the power n, right? So basically this will be phi t raised to the power n. Okay, very simple. So example, again, I use the normal 0, 1. So its phi t is e of minus t squared over 2. So suppose you have the sum, right? The Sn equals to the sum. Then the expectation of EITSN will be basically just by t raised to the power of n, e of minus nt squared over 2. So from here, you can see that basically this implies that its mean is 0. And the variance is n, right? So basically this one, the actual form is e of mu I, so I mu t, okay, I mu t. So this is a characteristic function for CF for normal mu sigma square, right? So that will be it's a negative. Actually, it's actually sigma square I square t square over 2. So basically, it's I mu t plus minus sigma square t square over 2, right? So here you do some matching, you can find that it is actually, yeah, so this implies that your Sn is normal with mean 0 and variance n, okay? Basically, this is actually already known. You can actually find this from elementary theory, right? Because the sum of n ID normal random variables will still be normal with mean equals to the sum of their mean, and the variance equal to the sum of their individual variances, right? So we got n ones here, so the variance is n, all right? Okay, maybe a few more examples. let's try the uniform. Yeah? If x1, x2, xn are uniform, 0, 1. Okay. So your phi t is basically, let's look at the individual case. Right? EITX. So this is basically 0, 1 EITX 1 dx. So it will be one IT EITX 0, 1 EIT minus 1 over IT. Okay. Sometimes we may actually, okay, so this form here, we may actually try to, there might be an alternative representation for this form. So let's see, if we try the following. Let's try and see what do we get. So you multiply this, you will get E of IT over 2 minus E of minus IT over 2. So this will be IT. Okay. So, and this one, basically you can write it as E of, so this can go up. This part here, you can write it as the hyperbolic sign, right? IT over 2 divide by, so basically this part here, you divide by 2 and then you cancel back with 2, so there's a 2 here. So it's IT. Okay, so you can actually get a different representation involving hyperbolic functions. Just to refresh you, the hyperbolic function is defined as the difference between two exponential functions. The hyperbolic cosine is the sum, and of course the hyperbolic tangent is basically just the ratio of the two hyperbolic functions. Okay. And sometimes you may actually want to make a representation using E of IT equals to cos t plus I sine t, right? Sometimes this is useful. So let's see, we can also have a representation as, if we use this is your de Moivre's theorem. I think the Moivre's formula. So then you have, you will be able to express this as cos t minus 1 plus I sine t over IT. And therefore you can have sine t over t plus cos t minus 1 over ti. And here you can actually multiply with I and I, so that the denominator will disappear. We don't want the I there, right? So you can, this will become minus. This will be I cos t minus 1 over t, right? So here you have your real part, and here you have your imaginary part, okay? Okay, you have a real part and an imaginary part. So sometimes this kind of representation will also be useful. Okay. So then we want, let's say, if our Sn is equal to the sum, right? So what is the characteristic function? So basically, your characteristic function will be BITSN. So basically, it will be E of IT minus 1, IT, the whole thing raised to the power of n. Okay. From here, if you some possible, okay, so once you got to this part here, um, um, this form may not be so okay. For this case, yeah, for this particular case, okay, this form may not be so useful because so here you're going to end up with something like this. Okay, or if you use this form, you will end up with 2 power of n e I n t 2. Okay. Right. So they are so this characteristic functions in this case they look a little bit complicated. All right. Anyway, obtaining them is actually just a simple application of the product rule. Okay. So basically, you just take the characteristic function of one of them, and then you raise it to the power of n. Right. So it'll be interesting to see what you can actually get from applying the so you have the characteristic function here, and it'll be interesting to see what you can get by applying the inversion formula, right? So you can get the inversion. You use the inversion formula, and you may be able to get something, some results about its PDF. Okay. In this case, we will not try it because the form is actually a little bit complicated, right? But for some other kinds of uniform distribution, it is actually possible to get a form, a workable form, all right? So just to let you know that. Okay, 0, 1 may be a little bit hard, but if you have something symmetric like plus minus 1, then you may be able to get some results. Okay. So for here, I will show you an example. If you have minus 1 and 1. Okay. So let's say your x is uniform minus 1, 1. Okay. So your characteristic function will be e of itx, okay, minus 1 to 1 times 1 over 2, right? Because you are uniform in minus 1 to 1. So the length here is 2. So you will have the height 1 over 2. So this will be x. And here you will have e of itx 2it minus 1, 1. Okay. So basically you have e of it minus e of minus it over 2 over it. Okay. And here you can, of course, have several representation. One representation is that this basically is a hyperbolic sine. Okay, and this one you can write it as minus I of sine, hyperbolic sine, and t here. Okay. All right, by multiplication of I over I. Yeah. Okay, this is one representation. The other representation is you look at this part here. Okay, you use the de Moivre's theorem. And what we will get? You will get basically cos t plus I sine t minus cos t. So cos minus t, yeah. This is a minus, yeah. Plus I of sine minus t. Okay. And this will be equal to cos t plus I sine t. Okay, so here, you just recall your elementary math, right? Elementary calculus about even functions and odd functions, right? So what are even functions and odd functions? Anybody remember that? What's an even function and what's an odd function? Anybody remembers? Small thing but important.
F inside negative x equal to fx for even function. Then odd function is f negative x is equal to negative fx.
Right, okay, that's right. Your even function means that if you change if the argument here, this is the argument, right? If your argument has a negative sign, it doesn't affect it. Okay, it's the same as you would get. It's the same as not having a negative argument, not having a negative sign. But odd functions, if you put a negative inside, your function will become minus. Okay, this property is very useful in some situations. Okay, so the common ones will be like, for example, your normal distribution, right? Your normal distribution is the PDF is actually even, right? It's even function because you look at here, right? What does it say? If you have, so this is your fx, right? So minus fx will be over on this side, okay? So basically they are the same, right? Okay, your f or minus x, that means on the negative. So this is your minus x, this is your x, right? So this is your f of x. It's the same as your f or minus x, right? So even functions, they are actually symmetric around 0, okay? They're symmetric around 0. Because of this, right, very frequently you can, let's say you want to integrate from minus x to x. Basically, you just integrate half of it and then you times 2, right? And then odd functions are useful because you see it minus, right? So one example is your sine function. Your sine is basically goes like this, right? Okay. So let's say you have this is obviously pi over 2. This will be minus pi over 2, right? So at pi over 2, right? The sine value is 1, okay? At minus pi over 2 is minus 1, right? So basically it's the sign will take out, okay? So basically if you take an integral from minus minus pi over 2 to pi over 2 is 0 because both sides, they have the same magnitude but different sign, right? So they'll cancel each other. Okay, you should always remember this although it's very simple, it will help you in doing integrals. Sometimes it will simplify the integrals. Sometimes if you observe something, because very frequently you have to integrate along the real line, right? And if you can notice that your function is actually odd or even, that can help you simplify the integral tremendously and help you make progress. Okay, if you don't know anything about odd functions, even functions, then you will get stuck because you don't know how to make use of the property of these functions, right? Okay, so although simple but very useful. Okay. All right, so let's get back to here. So we basically have, so here the cos is an odd function, yeah? Cosine is an odd function. You can verify that yourself, yeah? So cos is odd, so you have cos t. So sine is, cos is even, right? Sine is odd, so we'll minus I sine t, okay? So your cos t and cos t will disappear, cancel each other. So here you will get I times 2 times of sine t, okay? So in fact, this part here will simplify to I sine t, right? You simplify to I sine t, and yeah, included the 2 will cancel these 2, right? So you get I sine t, and then even nicer, right? Your I here will disappear, will cancel. So in fact, your uniform, right? It has a very nice characteristic function, which is sine t over t. All right, and you know the sine t over t is a classic example in calculus. So it looks like this. So basically it dampens, right? You know it dampens because your t is getting larger and larger, right? So it will, the denominator is becoming larger, right? And your sine t is bounded between -1 and 1, right? So basically it is it's kind of like dampening already, right? Because if you don't have a t here, then basically it will just if you don't have a t there, of course it will be just your sine going like this, right? But so once you divide by t, then it has a dampening effect here, right? Because as t tends to infinity, this will tend to 0, right? Okay, as t tends to infinity, okay? Now the interesting part is when your t tends to 0, so you will end up with yeah, 1, yeah? So this is the classic case. I think in one of the tutorial, maybe, okay. So this is this has actually a geometric, it has a geometric basis, right? Or if you use infinite series, then infinite series for sine t is t minus t cubed 3 factorial. So it's all the odd powers divided by t. So basically you get 1 minus t squared over 3 factorial and so on. So basically all these terms are related to t, and when t tends to 0, this whole bunch goes to 0, you're left with 1. Right? So the graph is like this. Okay? So this is the graph of the characteristic function, yeah, for uniform -1 to 1. And of course, if you want to find e of t x1 until xn, that would basically be just e of t x1, right, raised to the power of n. So basically that will be, if you use this representation, you basically will just have sine t over t raised to the power of n, right? It's very clean and compact, right? And of course, this is also possible, yeah. Right? This is also possible. You will just end up with something like shine t raised to the power of n. Then you have a minus I power of n. Right? They're actually the same. Okay. All right. So basically, yeah. So you might in fact establish certain identities, right, based on this relationships. Okay. So here, okay. So this example shows you that you have this situation, right? If your uniform is actually symmetric around 0, then you basically get something nice. Okay. You might actually want to think about, if you apply the inversion formula, what is going to happen, right? So you might actually think about that. Okay. And of course, we will actually just try to verify. Let's try to work out some moments, right? Just work out the moments for one case. Okay. Let's say so what is the so the mean of x must be 0, right? Because this is symmetric around 0, is uniform. So we already know it, the mean is 0. Okay. We can just try to use the characteristic function, all right, a little bit just to verify it. Okay. So you can either use the sine t over t or this form, right? Okay, let's try this one. So you differentiate d of dt sine t over t. So you will get t squared t cos t plus sine, sorry, it's minus sine t, okay, times t, times 1, right? So this is the derivative, right? If we try to, okay, so then we try to, we can't actually set it to 0 because here you end up with a case of 0 over 0. So basically it is a limiting case, right? Limit t tends to 0. All right, so this is t. So basically you want to use, let t tend to 0, right? Instead of plugging in t, because it doesn't work, yeah? Right, you'll get 0 over 0. So when you take limit, of course, since it leads to 0 over 0, you can apply L'Hopital's rule. So L'Hopital's rule, so you get d2t here. So here you get t minus sine t plus cos t minus cos t. Okay. All right. Okay, so here you will cancel the cos t. Okay. But then you will still end up with a 0 over 0 situation. So never mind. You apply L'Hopital's rule another time. So basically, so you differentiate this, you get 2. So then you differentiate your term here, right? Again, you get t cos t plus sine t, right? So now it's clear that it is going to be equal to 0. Okay. So this is if you use this particular form. Now, if you use this form, d of dt, okay, that will be, so that thing will give you minus I of following, t square, so you get hyperbolic, right? The derivative of the hyperbolic sign is the hyperbolic cos, right? It's analogous to your differentiation of the sign. So again, here if you have so what is this? Actually, is there an IT? Sorry, it's T. Okay. Oh no. Okay. Bit of a mistake. Okay. Right. It should be like this. Minus I. Okay. So this is t square, right? T hyperbolic cosine minus hyperbolic sine. Okay. So again, this will have the situation. So this is actually kind of like similar to this case, right? Where basically you still have a 0/0 case. So you will have to apply L'Hopital's rule on the numerator and the denominator, right? And so you can try that, right? I'll just leave that to you. Okay. So you should also get 0. Okay. All right. Okay. So so let's take a 10-minute break. All right. Have you looked at spectrum for continuous assessment too?
Yes, doctor.
Right. So do you have anything you want to ask about that? Okay, yeah, I know about the week 10 video because I want to do I want to make a recording of one of the tutorial discussion problem and then kind of like cut it into the video, right? Before I upload it. So that will take a bit of time, right? Because otherwise, I think there's a segment of it where one of the questions, right? I think it's question 2, yeah. Where actually I actually left out some information when I copied the question. Okay. So and then there's a bit of a notational mistake. So that's why I was not able to do it because the information given on the sheet was actually not accurate. All right. So after I checked back again, I fixed the problems. All right. So then I want to maybe make a separate recording of that and then cut into to replace the previous discussion on that particular section, right? So that just to make it complete. Okay, so that will take a bit of time. Please wait a bit. Okay. Okay, anyway, you can, if you haven't looked at the tutorial, sorry, if you haven't looked at continuous assessment 2, look at it now, all right? There are, I think, six or seven questions, right? So you have about 2 weeks to do that, okay? Right, okay. And then this Thursday, we're going to talk about the tutorial 7. All right, and then there will be one last tutorial next week for characteristic functions, right? After that, we are done with the tutorials, okay? And then you can prepare for your test on week 13 and 14. So the week 13 test has 20%, all right, and then the week 14 test has 40%, right? So each of the tests is allocated 24 hours, right? And it's open book, okay? So the you will find the video recordings, of course, useful, right? For studying, okay? So, but then if you had attended all the lessons online, right? Then you will roughly have a good recollection of what was covered during what week, right? Then if you want to search back for certain video recordings and then listen to it more carefully, then it's easier. On the other hand, if you had not listened to any of the videos, right, just sign in and do something else, okay, then you will find that it will be overwhelming. Yeah, you don't know which video recording to actually listen to, and then you may panic. All right, so just to let you know that. Okay. Okay. Are there any more questions you want to ask? Otherwise, we can stop here for today. Any more questions? Okay, so I think, okay, that's all for today. All right, so I will end the recording now. All right, thank you for listening.
Thank you.
Okay, thank you, everyone.